So at the beginning of this chapter, we introduced the equation and the graph of a sphere, and then yesterday we introduced the equation and graph of a plane. So our focus for today is to introduce a few more equations and graph for commonplace 3D surfaces, such as paraboloids, ellipsoids, cones, cylinders, and what are called hyperbolic paraboloids, which looks a little bit like a Pringle. Now, I've debated whether or not the material of today is something that you need to memorize. I think that the answer to that question is partially dependent on when you intend to take 254. If you're planning to take 254 in an online capacity, you probably will not need to memorize these graphs and surfaces. In a situation where you would need the graph and surface, you'll probably have access to an online graphing calculator that can get the graph for you. However, if you are planning to take Math 254 in a face-to-face capacity, then yes, I would recommend to memorize the following equations and their associated graphs, because you might need them in an in-person exam where you don't have access to a computerized graphing calculator. Today what we're going to do is identify the graph and equation of some of the most common 3D surfaces, the kind of stuff that you will be looking at, especially in Calculus 4. We're going to examine what are called the traces and the level curves of a 3D surface, which is basically just a topographical map of the surface. Then we're going to get some practice, primarily in the exercises for today, matching the equation of a surface with its graph and or its contour map. Now let's recall from yesterday that just in general, the graph of an equation is a visual representation of the set of solutions to the equation. The graph is the set of all solutions to the equation, which is all the pairs or triples of numbers that can be plugged into the equation, resulting in a true statement. So a point is included on a graph if it makes the equation true. And yesterday we looked at the particular example of the graph of the equation x squared plus y squared plus z squared equals 9. This described a graph which had the shape of a sphere. A point was included in the graph if its distance from the origin was exactly 3 units. XYZ is on the graph if it makes the equation true, and because this equation came from the distance formula, this happens if it is a distance of 3 units from the origin. And thus our graph had this shape, spherical shape, centered at the origin of radius 3. So let's work through the following table of some other equations, and let's look at their graphs via a computerized graphing calculator, and let's see what their graphs look like. Now, the kind of nice thing about all of the shapes that we study in three-dimensional space is that they're generally pretty natural extensions of corresponding shapes in two-dimensional space. And our first example of this is the so-called paraboloid. This is the three-dimensional version of a parabola. Now, the quintessential paraboloid in three-dimensional space has an equation of this format. Z equals some number times x squared plus some number times y squared. Now, the paraboloid is the three-dimensional version of a parabola, and the equation for a parabola had a very similar format. Instead of z equals x squared plus y squared, we just had two variables where you had the output y equals the input, the only input, x squared, and it had this sort of bowl shape. Now I've graphed the 2D graph on Desmos. To graph a three-dimensional graph, I typically use one of two websites. And the first one that's really convenient is the GeoGebra website. How do I get here? I usually, to be honest, I just go to Google and type in 3D graphing calculator, and GeoGebra is one of the first results. And in this case, I've typed in the three-dimensional extension of the parabola equation. No longer y equals x squared, but z equals x squared plus y squared. And creates the same sort of bowl shape, but that bowl shape has just been extended so that it's three-dimensional. So not a 2D cutout of a bowl, but an actual three-dimensional bowl, or the top of a marker if you prefer. Now, another website that can be really helpful for getting an idea of the shape of the graph is this 3D Surface Plotter website. I like this one because you can really easily see the z value at any point by looking at the color of the location on the graph. Generally speaking, warmer colors represent higher z values, so this can be a useful site as well. But I find that you do have a little bit less control over the range of the graph on this website, so it may be a little bit harder to see the shape of the graph in full. Here, this one looks like a little bit like a hammock, and it's harder for me to understand that this is actually in the shape of a marker tip if you extend the graph a little bit further in the vertical direction. So here is a paraboloid. Basically just take the two-dimensional parabola, spin it around like a surface of revolution, spin it around the vertical axis, and you get something in the shape of a paraboloid. The next 3D surface that you're prone to encounter is that of a sphere or an ellipsoid. It has the form x squared over some number squared plus y squared over some number squared plus z squared over some number squared equals 1. So basically the exact same as the equation of a two-dimensional ellipse, except since we're in 3 dimensions this time, we have an extra term corresponding to the extra variable z. Now an ellipsoid contains spheres as a special case. A sphere is just an ellipsoid where the amount of stretch in every direction, x, y, and z, is the same. So you get a consistent radius in every direction. Whereas an ellipsoid, just like an ellipse, allows you to be stretched out a little further in one direction than in another. So looking at a graph in 2 dimensions for a 2-dimensional ellipse, we could, for example, take 1 equals x squared divided by 2 squared plus y squared divided by 3 squared, and we get an ellipse which stretches out to plus and minus 2 in the x direction, and which stretches out to plus minus 3 in the y direction. If I went to GeoGebra and plotted the same thing, but with this extra z term, maybe I'll add on z squared divided by 4 squared, we get an ellipsoid which stretches to positive 2 in the x direction, that's on the red axis here. It stretches to positive 3 minus 3 in the y direction, and corresponding to the 4 squared under the z squared, the ellipsoid stretches to plus minus 4 in the z direction. So an ellipsoid is the extension of an ellipse, looks a bit like an egg or like a slightly distorted sphere. Next up we have the cone. The cone is the 3D version of the absolute value equation in 2-dimensional space. This one is almost the same as the equation for the paraboloid. However, the equation for the cone has a square root on the expression on the right, whereas the paraboloid has no square root, and it's just a polynomial. To see the connection between the cone and the absolute value, it may be helpful to remember that if you take y equals the square root of just x squared, then the square root and the x squared will cancel, but there is a slight price to pay. Because potentially the x value is negative, and if you take a negative x value, square it, and then take the principal square root, that negative value is going to change to a positive value. Therefore, the square root of x squared is equivalent to y equals absolute value of x. Now, if we have not just x squared under the square root, but if we add in a second variable, and we consider instead what happens if we get z equals the square root of x squared plus y squared, then that absolute value v essentially gets spun around to create this cone shape. Here, from a side angle, you can see the v, and the v got spun around to create a three-dimensional surface in the shape of a cone with the vertex here at the origin. So the cone with x squared plus y squared under the root is the 3D equivalent of the absolute value equation with just this single squared variable under the root. So let's move straight on to the hyperbolic paraboloid. Now, in some ways, this is the 3D equivalent of a hyperbola in two-dimensional space, although I think the connection to the hyperbola is not quite as straightforward as the connections that we've seen in the previous surfaces. The difference between a hyperbolic paraboloid and a paraboloid is that a hyperbolic paraboloid has the two variables subtracted after they're squared, x squared minus y squared, or in the reverse order, y squared minus x squared, as opposed to the regular paraboloid, which had the shape of this bowl, which had a plus in between the two terms. They were being added. Now, when you subtract the two squared variables, a really cool shape is formed. It looks like a saddle or a Pringle, depending on your personal taste. Here I am on 3D surface plotter, and I've graphed the equation where x squared is positive and y squared is being subtracted. Now, this equation is graphed here, and you can sort of see that saddle shape because the x squared is causing a curving up in the x direction, whereas the y squared minus y squared is causing a curving down along the y-axis here. It's sort of like an upward-facing parabola in one direction and a downward-facing parabola in the opposing direction. We can also see the shape here on GeoGebra, although I think this shape is slightly harder to read on GeoGebra than it is to read on 3D surface plotter. So this is just an example of the fact that different graphing calculators have different levels of usefulness depending on what kind of shape you're trying to understand. So if one of them is a little bit illegible, try the other one and see if it is more comprehensible to you. The final three-dimensional surface is that of a cylinder. A cylinder is a circle that's been extended and stretched out to live in three-dimensional space. Now, cylinders can be a little bit tricky because the equation of a cylinder looks exactly the same as the equation of a circle. Remember that a point is on the graph of an equation if the point makes the equation true. In this case, because we're in three-dimensional space, the graph contains three coordinates, x, y, and z. So x, y, and z in three-dimensional space is allowed to be on the graph of x squared plus y squared equals r squared. Well, the only real requirement is that the x squared and y squared satisfy the given equation, and z is free to do whatever it wants. The equivalent to this in two-dimensional space would be given by the following. Something like not x squared plus y squared equals radius squared, but if we just had x squared equals 1. This equation is satisfied by any point whose x-coordinate squares to positive 1. So any x-coordinate equal to negative 1, any x-coordinate equal to positive 1, as long as your point satisfies that condition, it makes the equation true, and therefore it's on the graph of the equation. So y is free, and we see this graph being extended infinitely in the vertical, the y direction. As long as x is negative 1 or positive 1, y can do whatever the heck it wants because y does not have anything to do with the equation that we are graphing. And here we see the equivalent in three-dimensional space. If we have an equation x squared plus y squared plus 1 being graphed in 3D space, then the variable z has no effect on whether the equation is satisfied or not. As long as x and y live within this circle of radius 1, then z can have any value and the equation will still be true. As a result, this graph gets extended infinitely in the positive and negative z directions, just as this 2D graph was extended infinitely in the positive and negative y directions. So just be careful about that. When you're graphing an equation, you need to know in what dimensional space are you graphing it. If you graph this circle in two-dimensional space, it will just look like a circle. But if you're graphing the same equation in three-dimensional space, that circle gets stretched out infinitely in the positive and negative z directions, giving you an infinite cylinder. Now, when you're graphing an equation in three-dimensional space, trying to get a sense of how it's shaped, sometimes the graph is such a huge and horrible mess that even the graphing calculator's rendition can be difficult to interpret. Not only that, but sometimes, for example, in an in-person exam, you just might not have access to a three-dimensional graph, computerized graph of the surface. Not only that, but the 3D graphs are really hard to read when they're just static images as viewed from a single perspective. When we were looking at those 3D graphs online just a few minutes ago, I had the ability to click and hold and drag my mouse around to rotate the surface and see it from all angles. Without the ability to do that, it's really hard to get a read on the surface. For all these different reasons, it can be useful to get a representation of a 3D surface in terms of a two-dimensional picture, so that you can read a static image and get some information about the graph's appearance and nature. Now, this is the equivalent in real life of a so-called topographical map. I just had to correct that typo. Topographical map, not topological. That's a totally different thing. You won't study that for a good long time. A topographical map is used to represent terrain and different elevations of terrain in terms of a easy-to-read two-dimensional picture. So here's an image courtesy of the REI Co-op. If you have a landmark that looks like two hills of these different heights, then the topographical map would represent all these different elevation lines as curves in two-dimensional space. The elevations corresponding to those elevation lines are indicated with just a number that's printed on the curve itself. So by looking at the elevation lines and by looking at the printed number, you can go backward and reconstruct in your mind, okay, all the points on the green curve correspond to a location in real life where the height is 1,440 maybe feet above sea level. The analog to one of those elevation curves in the topographical map, in mathematics we call such a thing a level curve. A level curve of an equation corresponding to a particular given c value. Maybe it's z equals c. This is all the pairs of x and y values, all the horizontal location, that correspond to this particular given elevation, this particular given z value, this particular given height. All the pairs xy paired with this given z value by the equation. For example, suppose that someone was considering the equation z equals x squared plus y squared. Now, do you remember which shape was given by this kind of equation? Remember, this one is the paraboloid. Variable z is equal to the sum of the squared variables x squared plus y squared, the 3D equivalent of a parabola. If someone was interested in the level curve corresponding to z equals 1, they're asking for all the points x and y, which are paired with z equals 1 in the equation. So this can be found by going into the equation, replacing the z with this given number of 1, and describing all the values of x and y that make that equation true. In this case, the level curve corresponding to z equals 1 is a circle of radius 1. Going back to our 3D surface plotter, here is our paraboloid z equals x squared plus y squared. And what's nice about this particular website is that different z values are indicated on the graph by color, which makes it a lot easier to see the level curves on this website than on the GeoGebra 3D graphing calculator, for example. Z equals 1 seems to be, roughly speaking, around this cyan band of coloring. And if we look top down at the graph, we can see that this cyan band of coloring, corresponding to z equals 1, does form a circle in terms of x and y values. So that's a more conceptual way to think about the level curve, in terms of heights or elevations. The level curve corresponding to z equals c is the set of all points on the graph with a height / elevation of this value c that's given to you for the z value. Now, one quick definition. We have the term topographical map. In mathematics, we usually refer to this as a contour map. A contour map is a graph of several level curves. So a contour map is going to look a lot like this topographical map taken from the REI Co-op, a two-dimensional picture where the different level curves are drawn and are labeled with the corresponding elevation / z value. So let me show you how to draw a contour map for a particular surface in the following running example. Someone says construct a contour map for the surface formed by graphing z equals e to the power negative x squared plus y squared. Now, fear not. This is not one of the surfaces that should be memorized. This is not one of the canonical 3D surfaces that comes up very often. But nevertheless, let's see if we can create a contour map for this surface and construct a two-dimensional representation of that graph. Now, the question gives us some further instructions. In your contour map, make sure to include the level curves that correspond to z equals e, 1 divided by e, 1 divided by e squared, and 0, when possible. Bear in mind that a graph may not ever reach a particular elevation. In which case, the level curve, the set of points which correspond to that elevation, is just empty. So that is possible. Always be on the lookout for that. So let's begin with z equals e. To find the level curve corresponding to z equals e, I'm going to take the given equation and I'm going to plug the value in for z in the equation. So the first one I'm asked to investigate is where z is equal to e itself. Now I have e to the something equals e to the something. This can be solved by getting rid of basically the base by applying natural log to both sides. Natural log destroys e. Natural log of e by itself simplifies to 1. I get negative x squared plus y squared. In other words, minus 1 equals positive x squared plus y squared. However, because x and y here are intended to be real numbers, you can't square two real numbers, add them together, and get a negative result. So this is empty. And that means that in the contour map, we would not draw anything at all corresponding to a level of z equals e. It means that the surface never actually reaches a height that's equal to e. So having concluded that the first given level is not reached, that level curve is empty, let's go ahead and let's work on z equals 1. Okay, now an exponential function can only produce the number 1 when the exponent itself is equal to 0. So we found that x squared plus y squared equals 0 is required to get an elevation of 1 unit. Now this level curve is not empty, but this level curve is very, very small. The only way that this can happen, the only solution to this equation, is if both x and y are equal to 0. So off to the side, I'm going to begin to construct my contour map. And I'm going to graphically represent the data that we have just found. I'm going to indicate the singular point 0, 0 at the origin in two-dimensional space, because a contour map is a two-dimensional representation of a surface. And next to that dot, I'm going to make a note that this corresponds to z equals 0. Alright, this is after we've finished the entire exercise, but I just noticed that there is a misprint here, that I accidentally wrote z equals 0. However, the elevation corresponding to that point was z equals 1. So quick correction, the elevation of the point at the origin is equal to the number 1. This is just like the topographical map from the REI. We don't just graph the curves with no labeling. Each curve is labeled with its corresponding elevation. We do exactly the same thing on our contour map. Each level curve is labeled with its elevation, its height, its z value. Next, we're asked for z is equal to 1 over e. And a reciprocal like that is equivalent to an exponent of minus 1. So if I cancel the e's, for example, using a natural log, and I cancel the minus signs, then I'm left with x squared plus y squared equals positive 1. X squared plus y squared equals positive 1 is a circle of radius 1. To reflect that on our contour map, I'm going to draw in a circle of radius 1 in the xy plane. And I'm going to mark the elevation. The elevation of the points on that level curve corresponds to z equals 1 over e. And the next thing that we're asked to do is z equals 1 over e squared. Now, 1 over e squared can again be expressed as e to the minus 2. So using the same sort of algebra manipulation as before, this would correspond to positive 2 equals positive x squared plus y squared, which is a circle of radius equal to about 1.4. How would I indicate this on the contour map? I would draw a circle whose radius was approximately equal to 0.14. And here is z equals 1 over e squared. Something like that. And finally, we're asked about z equals 0. But if I plug 0 into z's position in the given equation, then I get something that has no solutions. You cannot apply natural log to this because natural log of 0 is undefined. So this is another empty level curve. It's an empty level curve, which means that this graph never reaches a height of 0. So let's take a moment and think about what we have concluded. We got to conclude that this graph never reached a height of e. The upper range of this graph is pretty small. Additionally, this graph seems to never have reached z equals 0, so it doesn't go that low in the z direction either. Not only that, but it's looking from the contour map that the graph is getting smaller as you move away from the origin, descending from 0 to 1 over e, and descending even further to 1 over e squared as we move away from the origin. And you can see this confirmed on the graph of the GeoGebra 3D graphing calculator. I would say this is one of those graphs that is somewhat difficult to interpret correctly, but using this graph together with what we studied when we were doing the contour map, we can get a much clearer picture of what's actually going on. This graph's maximum z value seems to be at around z equals 1, which does confirm what we found on the contour map, where z equals 1 was basically our highest elevation, and that was achieved at the origin, dead center in the graph. We also see that the graph is smoothly descending from that top of that hill in every direction. So it makes sense based on that our level curves would have the shape of circles, because regardless of which direction you descend from the top of the hill at the origin, the z value decreases by the same amount in every direction. And then somewhat mysteriously, we have the entire rest of the graph, where it's basically almost planar. It is living not on the xy plane, but just above it. We know that the graph never actually crosses the xy plane because the xy plane has a z value of 0, but we found that the level curve corresponding to z equals 0 was completely empty. And that's how we can know for sure that this graph is completely above the xy plane at all times, probably asymptotically getting closer to the xy plane, but never actually reaching it. Now, one of the nice things about the 3D surface plotter in particular is that because those graphs are color-coded according to the point's z value, it can be really easy to get a contour map by looking at a top-down view of that 3D surface plotter graph. For example, here I am on 3D surface plotter looking at the graph of the hyperbolic paraboloid. If we wanted to get a sense of what the contour map for this thing looked like, then what we can do is we can take this graph and rotate it using our mouse so that we're looking at it top down. I'm going to look at it top down so that according to the tradition for our notation in the xy plane, that x is going horizontally and y is going vertically. Now across this center band of points here in green, Green is corresponding to a z-value which is approximately 0. And by clicking the point on the graph and looking at the coordinates of that point, we can see that the z is given to us 0 at the green location. Whereas over here in orange territory, we're getting closer to z equals 2. In red territory, closer to z equals 4. In blue territory, where the colors are getting colder, it's the same behavior except it's looking to be negative. Z equals approximately negative 2. Z is approximately negative 4. I can make a really quick and dirty sketch of the contour map for this graph. Z equals 0, colored green, had the shape of an X. Z equals positive 2, in yellow, had the shape of a hyperbola in the X direction. Z equals 4, in red, had the shape of a more distant hyperbola in the X direction. Z equals minus 2, and Z equals minus 4. Now, a final bit of terminology whose usefulness, I would say, is limited. I don't see this used quite as often as level curves. From time to time, instead of looking at all the points with the specified height / z value, it can be useful to look at the set of points with the specified x value or a specified y value. In this case, the curves that you get are called traces rather than level curves. Level curve is a term specific to when z is a given value. Traces includes that you might have a specified x or a specified y. Now, traces may be more appropriate in situations where either x or y is the isolated variable instead of z. For example, here we have an equation where y is isolated and it's equal to the positive square root of 9 minus x squared minus z squared. Now this is a hemisphere. It is related to the equation of a sphere, as you can see by squaring both sides and doing some rewriting. But it's only half of a sphere because this equation forces y to be greater than or equal to 0 because it's defined in terms of the principal square root, which is never negative. So the graph of this is a sphere, but only the half of the sphere with a positive y value. In this case, if you were trying to get a read on the behavior of this graph, trying to create a two-dimensional representation of that, it might be more appropriate to use traces. To set y equal to certain fixed numbers, and look at the values of x and z that would be necessary to make that equation true. For example, for a very quick example, if I was looking for the level curve corresponding to y equals 0, I would go into the equation, I would set y equal to 0, and then I would investigate the values of x and y necessary to make this true. Do a little bit of arithmetic, and this is equivalent to x squared plus z squared plus 9, which is a circle of radius 3, not a circle in the xy plane, because y is not in this equation anymore. Instead, a circle in the xz plane of radius 3. So I would sketch in that circle. I would label it with its corresponding given value, y equals 0 for this curve, for this trace. And you can begin to construct a contour map for these different values of y, using very much the same technique that we used for level curves. It's just that instead of being given z equals a number and plotting the solutions on the xy plane, you replace either x or y with a given number and plot the solutions on the either XZ plane or the YZ plane. I'll leave the rest of this to you as an exercise. It's very, very similar to the process of finding level curves, just with a different variable. To sum up what we did today, we examined the graphs of a few quintessential three-dimensional surfaces, and we thought of them as the natural extension of some familiar functions and graphs from two-dimensional space. We looked at two different online graphing calculator websites that each has their own purpose and usefulness in terms of understanding a graph. And then we looked at a two-dimensional representation of a 3D graph by graphing a contour map, the mathematical equivalent of a topographical map of elevations of terrain. A contour map is a two-dimensional picture of a surface showing all the points that achieve certain z values.